I'm Parker Kai. This is Opalite, a real-time assistive perception system for blind and low vision users. The idea is really simple. If you are blind, you don't want to have a long caption of a room. You just want a short answer. It should be fast enough to act on, like stairs ahead, door on your left, that kind of short, useful information. So most apps today only handles one piece of that pipeline. We have OCR in one app, and then we have like ChatGPT or Gemini Live to describe the room, describe the scene, and navigation is something else. So Opalite here puts the whole loop on one device, and it's built around an Intel RealSense depth camera with a small local language model on top. I will work through how it works, and then I'll show you a quick live demo. The system is built in 3 layers, all share one C++ core. Phase 1 is the foundation, a desktop app that takes the depth camera, runs the depth through what I call free space analyzer, and figures out which direction is open. You can see the live color frame, the depth frame, and then the top-down view all at once. Phase 2 has 2 parts, Phase 2A and 2B. 2A adds the sonar system inspired by bats. The program generates a continuous stereo hum that gets louder when you approach something. For example, the closer you get to an obstacle on the right, louder hum in the right ear. The user can fill the space with audio feedback. Phase 2B adds what I call the brain. That is the system that user actually talks to. It's a local Gemma 4 vision language model running through Ollama or llama.cpp. When the button is pressed or a question is asked, you get a spoken answer back. Phase 3 takes the whole thing, the geometry, the sonar, the brain, and compiles it for an Android phone. So we can plug in the depth camera into the phone over USB-C, and you are getting a wearable version of the same system. That dash box in the diagram here is the C++ core code that compiles into both the desktop binary and the Android library. It's the same source, 2 outputs. So, and the design rule is written right here. Geometry runs every frame, VLM only on demand. Let me zoom in on the geometry analyzer, the safety critical piece of the system. To iterate on it, I built a simple desktop UI. This is a live color view on the left, the depth view on the right, and a top-down map on the bottom. The top-down map is made by projecting every depth pixel into a metric ground plane grid, basically a bird's eye view of where things are around the camera. The green-red color overlay that you see here in all of these are left, center, right, 3 sector cones. I fortified the analyzer 5 times based on things that kept failing during live testing. First, I only look at the middle 50% of the depth frame. Ceiling and floor color shouldn't get a vote in the steering. Then I make the 3 sectors non-uniform. The center beam stays narrow because I only care about what's directly in front of the user walking path. And the left and right sectors are wider because their job is just to steer, and they need enough peripheral view to actually tell which side is more open. I started with 3 equal regions, but it just didn't work because the uniform angle differences does not make sense when changing the directions. And inside each sector, instead of trusting the closest single pixel, I use the 5th percentile of the valid depth pixels. That way, depth pixels can mark a whole sector as blocked. I also require at least 200 good depth pixels before I trust a sector at all. If we encounter some glossy material like a glass wall, it would say insufficient data instead of falsely calling it blocked. And last one is the sticky center bias. For example, if right and center are both open, the system keeps the center as the suggested direction, unless a side really beats it by at least like a quarter of a meter. This stops the steering from flickering between the both options. And here, the clearance score is just a clamp linear function. It's a depth between half a meter and 3 meters, maps to from 0 to 1. It's very simple, deterministic, and very fast. Here you can see the analyzer screenshot from before and after the hardening. You can see that on the glossy door reflection here, the depth camera fails and shows some black depth pixels. On the right, the after version doesn't react to the same noise. The right direction cone is open as it should be. The brain has 2 modes, and choosing between them is honestly one of the most interesting design call in the whole project. If the user asks a directional like where, how far questions, for example, where's the door, how to find the sofa, how far is the table, etc. I use the locator mode. I force the model to return just two things, what the object is and which side it's on, left, center, or right. Then I go back to the depth sensor, read the actual distance, and stitch the sentence together. So the end result would be chair on the left, about 1.5 meters. If it's anything else, such as describe the room, what's in front of me, that sort of question, the freeform mode will kick in and the model writes the whole sentence. But I still need to do some prompt engineering to make sure the answer is free from the defensive filler words like the image shows, etc. Here's the key idea. In the locator mode, the language model detects the object and picks the side, but the depth sensor confirms the distance at that side. So even when the model is doing the talking, the actual metric you hear is from the real measurement from the depth sensor. It reinforces the geometry first design principle. Okay, let's see it in action. Hi, this is a demo for the Opalite Edge app. So I have a same hardware, the RealSense depth camera. It's connecting to my phone via this USB-C cable. So it's powered purely by this cable from the phone. No extra hardware. So when I plug in, it will
Blocked
fire
at
up
0.2 meters.
The app has the same layout, so it has the color frame, depth frame, which is all live from the camera itself. And then
Blocked at
it
0.2
also has
meters.
this top-down view that kind of scans the 3D environment and shows up on a 2D map. On the sonar pane here, you can see there's some sound meter. So left, center, and right. So these are the sonar sound that is playing on my headphones right now. So if I have something on the left side, you can see it on the top-down cone. Then there's some kind of humming sound, and I can change as I'm going to walk through the space. The sound would interact and change. So that's how I can kind of as a visual impaired user can navigate through spaces. So kind of like a bat. So the pitch can change, the volume can increase or decrease. And then I could also use my voice to control these settings. So when I press the huge button here, it would listen to what I'm trying to say. So I'm going to try that. Sonar off.
Sonar off.
Sonar on.
Sonar on.
Okay, so I'm going to use the sound to navigate through this corridor. So I'll just listen, and then if I kind of
Blocked at
go
0.8
towards
meters.
the wall, and I would hear a lot of more sound. But if I kind of steer away from the noise, I could kind of go to the clear space. Okay, so as you see, if I kind of facing a clear area, the sound would go away. And you can see the cones is all kind of going out and all clear. So next I'm going to show you the VLM kind of voice features. So if I tap,
Recliner on the left, 2.9 meters.
it will show like the most important object from the scene. It was just gonna keep
Sofa on the left, 3.4 meters.
What's in front of me, basically. And then I can long press to kind of ask the model to give me some kind of scene understanding or look for a certain area of interest. So long press. What's in front of me?
A black chair and a white sofa are present.
And I can also ask, where's the black chair?
Black chair on the left, 2.9 meters.
So when I ask where or looking for a certain object, it would actually tell me the direction and then the distance based on the geometry that I got from the app, from the camera. So that's kind of grounded truth answers. And then I can try to look for the door. Where is the door?
Door on the left, 3.6 meters.
Okay, so I'm going to try to navigate to the door. So I'm going to kind of hug the wall here. I can hear the humming sound when I'm kind of hugging the wall on the left side, left ear. Then as I'm going to almost arrive at the door, it would...
Block at 0.8 meters.
I could hear the block feedback, so I know I'm there. Okay, so that's how user can kind of find places. Describe the room.
A room has a white sofa and dark wooden railing.
Where is the railings?
Not visible.
Where are the railings?
Wooden railing in front, 4.0 meters.
Okay, so I'm gonna go to the railings and the stairs. So I can hear there's something on my left, which is the chair here that's blocking my path. So I can just kind of go. If I kind of keep going, then I'm
Blocked
hear
at 0.8 meters.
And it got the block feedback. But I'm going to steer away. Then I can go in front to the stairs.
Wooden railing in front, 2.5 meters.
Okay, so that's the end of the demo. So that whole loop, the sonar system, the locator query, the freeform descriptions, they're all running locally on the phone. The only thing that hits anything beyond the phone is the bring query, which just goes to a host PC on the same Wi-Fi network. Here's some quick numbers from the depth hardware. The geometry pipeline runs at about 9mm/second per frame. The bring query takes about half a second round trip. In locator mode, it feels really fast because it's a lightweight model and it's highly optimized for visual language tasks. Freeform mode is a tiny bit slower because the model has to write a full sentence, but they all feel like instant. The steering is quite stable and stays on center, while the path is clear in general. When the center beam is actually blocked by a hand or a wall or something, anything within a half meter, it transitions to whichever side has more room. The sticky center bias keeps it from flickering between the options on noisy frames. Finally, the screenshot on the right shows the desktop GUI catching a hand in the center beam. The analyzer flags it blocked. Then its adjusted direction shifts to the right, and you can see the Brain's caption picks the same things up. It suggests the user follow the direction to the right, so the language model and the geometry are both saying the same thing. Quick on what doesn't work yet here. The active stereo depth has non-failure cases. It doesn't work on featureless walls, direction lines, glass with reflections, surfaces. When the depth dies, the system just says insufficient data instead of giving the wrong guidance. But the user does not lose feedback in those moments. The camera also sees forward only around 90-degree field of view, so it's not as good as a human eye field of view. Also, a formal user study haven't been done yet. And on Android, Brain still needs to call the host PC because mobile runtimes for the newer model like Gemma 4 aren't quite there yet. You can run the model on the phone natively, but the pipeline to route the request is not there yet. Future work here, record some dataset for replay, run a pilot or with blind user or low vision users, and then move the Brain on device once the Android runtime catch up. And we can try a different wider field of view camera that could give a wider steering range. The takeaway is on the right here. Geometry handles safety critical signal at depth frame rate in real time. The language model handles the language work only when you ask. You get the speed and reliability of the geometry plus the flexibility of a real language model, and it's all local. The code is at the GitHub link here. Thanks for watching, and thanks for the semester.